A black hole brightened by half in 20 minutes. What pushed it? Because some space is chaotic, not precise clockwork. Tiny nudges explode into big changes, so predictions wobble fast. Here is the deal in plain words today. Unpredictable means sensitive to starting conditions, not purely random. That sensitivity hides in gravity, magnetism, and ripping plasma flows. We can understand it, but we must respect the limits. An orbit changes after a dust puff, a flare, or jitter. Sometimes the wildness pays us with auroras and discovery. Sometimes it slaps satellites and scrambles radio and timing. Bottom line, space can swing quickly because its laws amplify whispers. Out beyond the atmosphere, space weather whips across entire skylines. Unpredictable here means chaotic and turbulent, not inherently lawless. This affects missions, power grids, and astronauts on every pass. Fields and flows interact nonlinearly, so tiny inputs balloon wildly. Gravity tugs, plasma resists, and magnetic lines twist like rubber. Energy piles up in layers, then unloads in sudden bursts. Solar storms are the easiest example, and they bite hard. A coronal mass ejection hurls billions of tons at Earth. It travels at hundreds to 2,000 kilometers per second. If aimed right, arrival time can swing by many hours. Rule of thumb, faster clouds are also less predictable on impact. Shocks steepen, magnetic drapes rotate, and reconnection patches switch on. Those flips change radiation belts and disturb long polar airline routes. Power systems feel it too, through induced currents in long lines. We measure solar wind speed, density, and field direction upstream, but the geometry keeps morphing while crossing 1,000,000 kilometers. So forecasts carry ranges, not guarantees, like coastal hurricane cones. In one storm, auroras dipped to Texas latitudes for hours. In another, satellites tumbled from drag spikes at low altitude. Net result, chaos spreads through space when forces couple and cascade. Under a dark Milky Way, dishes listen for cosmic metronomes. A pulsar is a spinning neutron star, sweeping radio beams. They matter because they time gravity, like galactic atomic clocks. Delays hint at ripples in spacetime and drifting cosmic plasma, but the path is cluttered, so the ticks arrive imperfectly. Electrons in space bend waves, creating flicker and arrival jitter. Multiple paths interfere and the pulse shape breathes with frequency. Magnetospheres also switch states, changing beam width within minutes. Astronomers call it mode changing, and it wrecks clean fits. We fight back with wideband receivers and dynamic scattering models. We also watch dispersion measure, which tracks total electrons crossed. It drifts by a few percent across a single season. Here is a concrete case with numbers, not hand-waving. The Vela pulsar glitched, spinning faster by about 0.02%. J400 in 37-4,715 shows, timing residuals near 1 microsecond on quiet days. During plasma lensing events, delays stretch by tens of microseconds. Arrays average many pulsars, reducing randomness while keeping the signal. That approach recently revealed a background of nanohertz gravitational waves. So the picture is clear: plasma and magnetism inject real unpredictability. Clocks exist, but the universe keeps nudging their second hands. Picture a galaxy halo draped with ghostly, curving stellar streams. A tidal stream is spilled stars, pulled from a smaller companion. These shapes trace invisible lumps of dark matter. A lumpy halo means satellites and a history of quiet cannibalism. The orbits cross resonances, so small tugs cause sharp deflections. Bars and triaxial bulges twist orientations, stirring chaos into paths. Close passages near clumps kick stars, carving gaps and spurs. Integrations show neighboring trajectories diverging exponentially with time. That is classic chaos in a gravity-only problem. Real galaxies add gas drag and cluster tides for spice. GD-1 carries a toothy gap, likely from a heavy intruder. Palomar 5 spreads incredibly wide, fanned by chaotic stirring. In models, a 10 million solar mass clump sculpts a notch. One pass shifts angles by a few degrees, instantly visible. Other times, the culprit is the central bar, sweeping resonances. Its pattern speed slides slowly, smearing one-sharp orbital families. Observers map stream wiggles, then invert them into dark substructures. The inference is messy, yet it corners the unseen mass. Bottom line, tangled streams act like seismographs for an invisible world. They are readable, but never perfectly predictable in detail. Between galaxies, rivers of gas thread the deep cosmic web. These filaments are highways of matter, feeding young star factories. Fueling rates set how fast galaxies grow, so this matters. Predicting that growth needs knowing which flows arrive and when. Flows slam into halos, forming shocks that heat, ripple, then leak. Vorticity grows at curved fronts, seeding turbulence that shreds coherence. Magnetic fields amplify in eddies, redirecting gas into braided lanes. Cold streams sometimes pierce hot halos, shielding inside their own walls. Small changes at the boundary pick winners between heating and cooling. Simulations show sensitivity, especially around galaxies near the critical mass. At that scale, two fates compete and outcomes flip unexpectedly. One halo gulps steady filaments and forms stars like a metronome. A twin halo chokes intermittently, after shocks cage the inflow. Velocities reach hundreds of kilometers per second along bright spines. Densities vary by orders of magnitude between knots and voids. Spectrographs catch these flows indirectly, as faint absorption fingerprints. Patterns jump night to night with different sightlines through clutter, so the picture is turbulent highways switching lanes without signals. We can forecast averages, but not the exact splash points. Galaxies thrive or stall, depending on these unruly intergalactic streams. Imagine a city-sized star with a mind-bending magnetic field. A magnetar is a neutron star, with fields beyond comprehension. Those flares dump staggering energy in milliseconds, with real effects. That energy batters space environments and challenges our physical models. Stresses build in the crust as twisted fields try unwinding. A starquake snaps the lattice and launches Ulfane waves outward. Near the magnetosphere, reconnection ignites, letting trapped energy escape explosively. The radiation front races, changing opacity as pairs materialize. Small differences in twist angle create huge differences in release. That is sensitivity embedded in the most extreme magnetic machine. On December 27, 2004, one aligned perfectly. SGR 1806-20 erupted with historic fury. It released about 10 to the power of 46 joules. The pulse saturated detectors and briefly ionized Earth's upper atmosphere. Later flares show subpulses, drifting on timescales of tens milliseconds. Those structures hint at reconnection islands, splitting and merging chaotically. We watch for precursors, but warnings are scarce and unreliable. Even so, patterns across many events suggest preferred stress thresholds. Bottom line, magnetars are predictable in bulk, yet wild in detail. Their tantrums teach plasma physics that no lab could ever reach. In a shattered nebula, knots race through smoky green filaments. A supernova remnant is expanding debris, stirring the interstellar medium. These shocks likely forge many of our cosmic rays. Those particles seed chemistry and spark auroras across planetary skies. The blast wave slams clumps which ricochet and curl into fingers. Rayleigh-Taylor instabilities mushroom, where light gas shoves heavier material aside. Magnetic fields wrinkle and strengthen, trapping particles that surf repeatedly. Where the shock ripples, acceleration efficiency changes from patch to patch. Turbulence cascades downward, and filaments break into foggy wisps. A tiny density bump can redirect a whole ribbon sideways. Cassiopeia A shows knots flying at 5,000 kilometers per second. Brightness flickers year to year, as cells compress then relax. Tycho's remnant shows stripes, possibly markers of amplified magnetic waves. Gamma rays jump unpredictably, following fresh pockets of fast particles. Simulations match broad trends, but not the exact bright knots. So observers map changes, then infer average acceleration recipes. Those recipes constrain how high the particle energies can climb. Meanwhile, individual filaments still wander like fish in rapids. Net result: debris fields encode order, wrapped in small-scale chaos. We read the envelope, not every squiggle, and still learn plenty. Back at the consoles, teams build forecasts that embrace uncertainty. A forecast here is a probability map, not a single line. Decisions need ranges, costs, and confidence together. We run ensembles, nudging starting points within measured error bars. Divergence across members estimates the chaos horizon for that system. Lyapunov times mark when small errors double, and then double again. For solar storms, that horizon often sits around 2 days. Beyond it, arrival windows widen and impact strengths blur. We combine models with data, using filters that update beliefs. Bayesian schemes weight each member, favoring those matching new measurements. We also learn from analogs, clustering past events by fingerprints. Tiny test: would you fly polar tonight, given a wide cone? If the probability peaks modestly, rerouting could still beat the risk. In practice, operators set thresholds and automate protective responses. Solar arrays tilt, circuits enter safe modes, and orbits adjust gently. Numbers help here, not slogans or bravado at control centers. An upstream monitor gives a 40-minute warning on average. CME arrival windows still stretch plus or minus 6 hours. Pulsar timing campaigns average decades to tame microsecond wander. Bottom line, we do not eliminate unpredictability, we price it in. That black hole flicker from the opening now feels less mysterious. It brightened fast because small shifts cascaded through a tangled engine. Space is lawful, but some regions amplify whispers into roars. We can forecast envelopes and then live comfortably inside them. Where chaos rules, patient averages and smart hedges still win. Where turbulence rages, patterns emerge when you step back a notch. Scientists lean into that mindset and build tools to match. Exploration continues anyway, with humility riding shotgun beside curiosity. If you want more deep dives like this, stick around. The universe is not random, it is delicately sensitive. That truth keeps us honest and keeps discovery pipelines flowing. Thank you for watching and for caring about the messy truth. There is always another wild patch waiting beyond the next star. See you in the next one.